Welcome. Let's take a look at the difference quotient. So what does the expression f of x plus h minus f of x divided by x plus h minus x represent? Right, well, that represents well, I don't know what happened there. Apparently my pen did not want to write. That represents the difference quotient. And we could simplify that. We could distribute the x and combine like terms in the denominator. Right? So that would be f of x plus h minus f of x divided by x plus h minus x. Right? And then the x's would cancel. So that would be f of x plus h minus f of x all divided by h. By the way, I'm not going to be using the space above, so if you need some extra space, you can have it. As the distance between the x values, x and x plus h, approaches 0, what happens to the secant line? Well, the secant line becomes the tangent line. What is the limit, as h approaches 0, of f of x plus h minus f of x divided by h represent? Well, that represents some important concepts in calculus. It represents the derivative. It represents instantaneous rate of change. Represents velocity. Now put it here. And it represents the limit of the difference quotient, which is the derivative. And so we're going to do a problem on the next page, because I don't have enough room on this page. But it's on the same page as you're looking right now. And it's this problem right here. Suppose f of x equals negative x squared minus 4x plus 1. We want to find the limit as h approaches 0 of f of x plus h minus f of x divided by h. So we have the limit as h approaches 0 of negative x plus h squared minus 4 times x plus h plus 1. And then I'm going to use parentheses so that I remember to distribute the negative sign to all the terms, because we're subtracting everything. Negative x squared minus 4x and positive 1. And that is all divided by h. I'm just going to expand it out in the squaring in my head and write everything down. You don't have to write it out separately. After a while, you get pretty good at doing that. All right, so x plus h squared is going to be x squared plus 2xh plus h squared, and then we just make everything the opposite because we have to distribute a negative sign. So this would be negative x squared minus 2xh minus h squared, and then distribute the negative 4 minus 4x minus 4h plus 1, and then distribute the negative. So that would be plus x squared plus 4x minus 1, all divided by h. And we can cancel out some terms, the negative x squared and the positive x squared, the negative 4x and the positive 4x, and the 1 and the negative 1. Actually, everything that doesn't have an h should cancel out. So then we have the limit as h approaches 0 of negative 2xh minus h squared minus 4h, all divided by h. We can factor out the h, so that would be the limit as h approaches 0 of h times negative 2x minus h minus 4 divided by h. Right, so now we can cancel out the h. So we have the limit as h approaches 0, negative 2x minus h minus 4. Now at this point we could substitute the 0 for the h and then drop the limit statement. So actually I'll put it over here. So then when we substitute 0, we have negative 2x minus 0 minus 4. That means that the derivative for negative x squared minus 4x plus 1 is negative 2x minus 4. All right, so now that's not just an equation. That gives us all kinds of information about our function and how it changes at different values. So we're going to do some investigation of the derivative in this particular series of nearpods. So your result to the previous limit is defined to be the derivative, f prime of x, of the function f of x. Now let's see what this derivative represents in terms of the graph of f of x. And that's in your notes already, all filled in. The only thing I did here that's not in your notes is I already graphed some lines. So the result of the limit as h approaches 0 of f of x plus h minus f of x times h for f of x equals negative x squared minus 4x plus 1 is a function in terms of x. The graph of f of x is pictured below. So it's f of x. That means that this is the graph of negative x squared minus 4x plus 1. And I don't think it's too difficult for us to figure out that it is not negative 2x minus 4. All right, so we're going to complete the chart for the indicated x values and f prime of x. All right, so what we're going to, actually let's do the bottom part first. It's easy enough. So use a ruler and draw a tangent line to the graph of f of x on the grid above at x equals negative 4, x equals negative 2, and x equals negative 1. And you try to make it so it's just intersecting, the best you can, intersecting the graph one time, just at one point. All right, so you can take care of that. Let's fill in the table, and then we'll come back to talking about those lines that we just graphed. So the x value is negative 4. Let's find the value of the derivative when x is negative 4. Well, that's pretty easy because we're just going to plug in a negative 4. Up into my parentheses. There we go. All right, so that's going to be positive 8 minus 4. That's going to be 4. And now let's find f prime of negative 2. So that's going to be negative 2 times negative 2 minus 4. Well, that's going to be 4 minus 4, and that's 0. And then let's one more. We got to negative 1, so that's going to be f prime of negative 1. And that's going to be negative 2 times negative 1 minus 4. So that's going to be 2 minus 4, so that's going to be negative 2. Now, compare those values to the lines that we've graphed, the tangent lines that we've graphed on the graph there. All right, so you notice that when we plugged in negative 2 into the equation for the derivative, we got 0. And if you look at negative 2, the tangent line is horizontal. It has a slope of 0. If we look at the result when we plugged in negative 4 into the equation for the derivative, we got a positive value. And notice it looks very much like the slope of that tangent line. And when we plugged negative 1 into the derivative, we got a negative value. And notice it's not as steep as the line is when we plugged in the negative 4. It's a little less steep, and it's negative, and it very much looks like it could be a slope of negative 2. Right, so by investigating the graph, what does it appear that the derivative function represents in terms of the graph at given values of x? the derivative now let's be a little bit more specific. Let's call it f prime of x. So that way we can just call the function f of x. So the derivative f prime of x gives the slope of f of x for any given value of x. You can think of the derivative as a slope machine. X values go in, slopes come out. Right? Right, so the definition of the derivative and what it represents graphically, you can add this to your notes. The derivative equals a slope of the tangent line. For a given, oops, I didn't want a period there. For a given value of x. Graphically, the value of the derivative tells us whether a function is increasing or decreasing. Or remaining constant. So increasing, decreasing, or remaining constant. All right, so we want to find the equation of the tangent line to f of x at each of the points below. All right, we already have the tangent lines graphed. We just need the equations. All right, so you need two things to write the equation of a line. You need slope, and you need a point. We've got the slope, right? We found the slope when we plugged into the derivative. So at -4, the slope is 4. To find a point, all we have to do is look at the graph, right? So when x is -4, looks like that point is -4, 1. Right, so our slope is 4, and the point is -4, 1. So then the equation is going to be y minus 1 equals 4 times x minus a -4, so that's x plus 4. Right? We can solve for y, so we have y equals 4 times x plus 4 plus 1. And if we want to write that in slope-intercept form, we can just distribute the 4. So that would be y equals 4x plus 17. Right? And if we look at the graph, right, it very well looks, I mean, the line is short. We didn't draw all the way up to where it would intersect the y-axis, but that seems quite reasonable to be the equation of that particular blue line, y equals 4x plus 17. All right, let's take care of the next one. All right, so we have the slope is 0, and when x is -2, y is 5. This is the point -2, 5. So we're writing the equation of a horizontal line. We really don't need to use point slope form. So m is 0 our point is negative 2, 5. Right? But no matter what x is, y is 5. So this is the equation of a horizontal line. This is the equation y equals 5. I mean, even if you use point slope form, you would still get y equals 5 because everything else is at 0. And then the equation of the tangent line at x equals negative 1. Right? So the slope is negative 2. And at negative 1, that looks like negative 1, 4. Right, so we have the slope was negative 2. And the point was negative 1, 4. So then the equation of the tangent line at that point would be y minus 4 equals negative 2x plus 1. Distribute the negative 2. We would, if we isolate y, we have y equals negative 2 times x plus 1 plus 4. And if we want to write it in slope-intercept form, that would be y equals negative 2x, negative 2 plus 4, that's going to be plus 2. And let's see if that seems reasonable for the line that we graphed. Okay? That does seem very reasonable. Like if we continued the line, that it would intersect the y-axis at 2. Right? So all we need is the derivative and any point, and we can write the equation. We can find the slope of the tangent line by plugging in the x value into the derivative. We can find the equation of the tangent line, right, given the derivative and any point on the graph. So when you hear derivative, you think slope of the tangent line. When you think slope of the tangent line, you think derivative. All right, so let's find a couple. And we're going to use the definition of the derivative, the limit definition of the derivative on these. All right? So we've got the limit as h approaches 0, 2/3 x plus h plus 3, and then we're subtracting 2/3 x plus 3, all over h. Right, so that's going to be the limit as h approaches 0, 2/3 x plus 2/3 h plus 3 minus 2/3 x minus 3 all over h. We've got some things that are going to cancel out. So we can cancel out the x's and the 3. And so the only thing we're left with, we got the limit as h approaches 0 of 2/3 h divided by h. Well, the h's will cancel out. And so that means the derivative is 2/3. And that makes sense. This is a line. What's going to be the slope of the tangent line? Well, then since the slope of this line is 2/3, the slope of the tangent line is always going to be 2/3. Right? So let's add that. Slope of the tangent line is always 2/3. Let's try the next one. Right, so we have the limit as h approaches 0. Yeah. 1/2 x plus h squared minus 2 times x plus h plus 3, I hope I can fit this in, minus 1/2 x squared minus 2x plus 3, all divided by h. So that's the limit as h approaches 0. And again, I'm going to expand and multiply at the same time. So this is going to be 1/2 x squared. So 1/2 times 2xh, that's just going to be plus xh. And then plus 1/2 h squared minus 2h plus 3. Squeeze it in, minus 1/2 x squared plus 2x minus 3. Oh, just squeezed it in. all divided by h, and aren't you glad some of these are canceling out? The x squareds will cancel out. The 2x's will cancel out. The 3 will cancel out. So that's going to leave the limit as h approaches 0. See, these polynomial ones aren't too bad. Xh plus 1/2 h squared minus 2h, that's it, all divided by h. Let's factor out the h, so we have the limit as h approaches 0 of h times x plus 1/2 h minus 2 divided by h. The h's will cancel. We'll squeeze this in somewhere. Right, so we can plug in the 0, right? So this would be the limit as h approaches 0, and we have x plus 1/2 0, or 1/2 times 0, minus 2. And that's going to mean that the derivative, f prime of x, is x minus 2. Right? Notice that its degree is 1 less than the degree of the original function. And, oh, this is, so here, this one I already have up. So notice that the derivative for f of x equals 2/3 x plus 3 was different than f prime of x for f of x equals 1/2 x squared minus 2x plus 3. How are they different, and why do you suppose this is so? I left this up here. And actually, I'm just going to do this. All right, I'll go this way then. Be that way. There we go. All right, so the derivative for the function was f of x equals 2/3 x plus 3. The derivative was 2/3. Notice that we have a constant slope for all x. That makes sense because the equation was a line. Right? It is always positive. Right? It is always increasing. So since the derivative is always positive, f of x is always increasing. Let's take a look at the other problem. Oh, this thing just hates me. All right, so f of x equals 1/2 x squared minus 2x plus 3. The derivative is x minus 2. The slope will change based on the x value. It could be positive if x is greater than 2, right? If I plug in 3, I get a positive number. It could be 0 if x is 2, or it could be negative if I plug in something less than 2. Like I plug in 1. 1 minus 2 would be -1. So our slope here is changing. It's not a constant rate of change because this is not a linear function. Well, that's all I'm going to do for in this video, and then come back and we'll see a little bit more about the derivative and context. Thanks for watching. Bye for now.